So, ladies and gentlemen, we are hopefully back live so that we can continue from where we left off before Google Hangout left us. We were looking at a simple system with two equations and in two variables, and our goal was to somehow convince ourselves that the operation, one of the elementary operations, namely you can add a multiple of one equation to a different one, preserves the number of solutions. So let's see what happens here. So let's assume that we have a pair of real numbers, S1 and S2, which is a solution to this system of equations. What does this mean? The fact that this is a solution means that if we plug in S1 and S2 for X1 and X2 respectively in the two equations, we satisfy both of them. That's what it means that this is a solution. Okay? So now let's see what happens if we, to a system of equations, which we obtain from the one that we have over here, by adding to the second equation d times the first one. So what is it that we get? The first equation doesn't change. And we replace the second one by the second equation plus d times the first one. So what is it that we get? We get b1 plus d times a1. And this is going to be the multiplying coefficient for x1. We have multiplied a1 by d, and we add it to the multiplying coefficient that we had before. For the second one, we have b2 plus d times a2. And this should be equal to what? C1 plus, C2 plus d times C1. That's the new equation that we get instead of the second one. We multiplied the first equation by d and added it to the second one. Okay, now my claim is that S1, S2 is still a solution of this system of equations. Well, there's nothing to check for the first equation because it's the same as before. And S1, S2 was already a solution of that one. That's the blue part. So that's okay. How about the second one? Okay, so let's plug in S1 and S2 for X1 and X2 respectively. And let's see what happens. So here we get B1 plus DA1 S1 plus B2 plus DA2 times S2. And what is this equal to? Okay, so we can distribute. So we have B1 S1 plus D times A1 S1 plus B2 S2 plus D times A2 S2. Yes? Oh, the question is, what does D stand for? D is an arbitrary real number that we are using to multiply the first equation. I said I'm going to add to the second equation a multiple of the first one. So D is an arbitrary real number that we use to multiply. These are all numbers. It's just that since our reasoning does not depend on what they are, we can leave them unspecified. You can think of it as a variable if you want. Okay, what now? So let's look at the red circled parts. If we sum these together, what do we get? we get C2, because S1, S2 was a solution to the equation, to the second equation that we had before. Is a solution to this. Okay, so these two together give us C2. Let me use a different color, plus. Okay, look at this green part. This green part tells us that A1 S1 plus A2 S2 gives us C1. And we are multiplying that by D. So what we get by summing these two summands here, we get D times C1. But lo and behold, this is exactly what we wanted this thing to be. So S1, S2 is a solution to the equation 2. Okay, you can go through the motions at home. You just need to calculate using summation and multiplication, which is something that you've done since you were at elementary school. So there's nothing mind-boggling here. It's just elementary school mathematics. Forget about discrete maths too. This is just plus and times. It's just to convince you that it is actually indeed true that that adding a multiple of one equation to another one does not change the set of solutions. So we are doing everything legally here. Our goal was to massage equations without changing their solution sets. That's why these three operations are there. And in fact, that's a little theorem that justifies the correctness of Gauss's method, and we've already done really the proof of correctness. Fantastic. And as an exercise here, you can use Gauss method to solve this system of equations. I'm not going to do it here now because we're going to be solving lots of different equations today. And it gets pretty boring if you do too many of those, because the pattern is always the same. Use the elementary operations to turn the system of equations into ones which is easy to solve, and then you do back substitutions to get the value for all of the variables. What I want to show you now is how you can actually teach this method to a computer, because this is what we are about. We want to develop algorithms so that the computer can carry out solutions of systems of equations. And in fact, a computer can do that because, well, there are lots of calculators that you could use that do it for you. And in fact, you can actually write the programs yourselves. So what is the science behind Gauss's method? And there are lots of exercises here, actually. So, well, let's do one exercise. Let's do one exercise. Otherwise, people say that I'm not putting my, following my, my motto that real teachers actually do examples. So let's do examples. Let's do one which is going to highlight one feature that we will need later on. Let's do the last exercise. I put lots of exercises on the slides so that you can also try them at home at your leisure. So let's write down this system of equations. On our scratch pad. And let's solve it now, using Gauss's method. So what we want to do is we want to use the elementary operations to turn this system of equations into one which is easy to solve. So one thing that first of all we might want to try and do is to try to get rid of this 2x here and this 2x here. What operation do you think I should try to use to get rid of those two x's? Well, one of your colleagues is saying division, which is something that I could do, but this would just turn the 2x into an x if I divide it by 2. So I would still have the x's around. I want to get rid of the x from those equations. Okay, so I can use this operation, as one of your colleagues is pointing out, the operation that says you can add to an equation a multiple of a different one. So if we actually multiply the first equation by -2 and then add the result to the second and the third equation, the x will disappear in both of them because 2x minus 2x is 0. So let's do that. So let me mark this for future reference. I'm going to take -2 times the first row. That's why I write -2r1. And I'm going to add that to the second row. And I'm also going to do the same. So I'm going to do two operations in one. -2 times the first row, and I'm going to add it to the third row. And let's see what comes out. First equation remains unchanged. Okay, the second equation becomes, remember now, let's first of all try to see what happens in blue here when I multiply the first equation by -2. Then this becomes -2x minus 6y equal to -2. And as you will see, even for these simple systems of equations, it's easy to make calculation errors. That's why you want a computer to solve them for you. Okay, so now let's add this thing to the second equation. 2x minus 2x gives me 0. That's what I wanted. Minus 6x plus y gives me minus 5y. Equal to what? -2 plus -3 gives me -5. Okay, so let's do the same. We add to the third equation, the -2 times the first one, which I marked there in blue. 2x minus 2x, 0. Fantastic. 2y minus 6y gives me -4y. This should be equal to -2 plus 0, so it should be equal to -2. Okay, at this point, we can already start seeing something. Spider sense is tingling. Do you think this system is going to have a solution? One of your colleagues is saying y appears to be 3. Let's see. One of the things that I can do is to multiply one equation by some non-zero number. So if I want to know what y should be, I can multiply, say, the second equation by -1/5. Or in other words, I divide by -5. So what I'm going to do next is I'm going to take the second equation and I multiply it by -1/5. Oh, sorry, not y here. I want to follow my... This should be R2. So what is it that I get? X plus 3y equals 1. And now I get y equals 1. Well, and suppose at the same time I multiply the third equation by -1/4. What is it that I get? I get the y should be equal to 1/2. Okay, Houston, we have a problem, don't we? Because y cannot be both equal to 1 and 1/2. So what conclusion do you draw? No solution. Yeah, I think we are getting into bullshit. But let me perform one more operation to highlight one thing that we will need later on. Suppose I add -1 times the second row, say, to the third. Let me put the result in red. Okay, so I get first equation doesn't change. Yeah, that should be a plus. Second equation doesn't change. First equation, the third equation becomes 0 equals 2 minus a half. And I want you to focus on this last equation that we have in this system. This is a telltale sign that something is wrong. Of course, we already knew beforehand, but we are humans, so we can easily do pattern matching. So, as you will see now, when we turn Gauss's method into science, that is to say, into algorithms, instead of human heuristic application of a method, you will see that whenever you have a situation in which you have an equation that says 0 should be equal to something which is non-zero, that's the telltale sign that tells you that the original system of equations does not have any solution. Now, this thing does not have any solution. We reached it from our original green system by performing operations that we have shown preserve the set of solutions. So since this thing there's no solution, this original green system of equation also does not have any solution, because everything we've done preserves the set of solutions. So since there is none at the end, there was none at the beginning. So far, so good. Any doubt about what we just did? I just wanted you to show, I wanted to show you an inconsistent system of equation to point out that this is sort of the telltale sign for inconsistency. That's the one we will be looking for. Whenever you see something like this, garlic necklaces, no, you don't want it. Even though we are not fighting vampires, sort of garlic necklaces always help. They're also good for your health, perhaps not for your relationships when you're trying to meet some interesting people in the pub. Okay, so how can we turn Gauss's method into science? And by the way, this is our good old friend, Carl Friedrich Gauss, prince of all mathematicians, as they used to call him. Also an algorithmician, as we will see. So these are the steps. I mean, algorithms are steps that we can follow as if we were mindless machines and get the right results, instead of using our ingenuity and actually screwing everything up. Okay? So let's follow the method. Step 1. We forget about the system of equations and we turn it into a matrix. We enter the matrix. Well, I mean, matrices are your friends. Some people here look like they're puking when they hear the word matrix. No, I mean, they are your friends. They are two-dimensional arrays. Bread and butter of programming. Here we are going to use them to solve systems of equations, and more, in fact, in this course. You will love them. You will have them tattooed on your forearms, unless you have already, at the end of these few lectures. So how do we do it? Well, this is not rocket science. If a computer can do it, so can we. We just basically look at the rows here one by one, and we write the rows in the matrix. So x1, x2, and x3, this will correspond to, each variable corresponds to a column in the matrix. And each equation will correspond to a row in the matrix. And what do we write? We write the multiplying coefficients one after the other. So for instance, here you have x1 plus x2 plus x3 becomes 1, 1, 1, because these are the multiplying coefficients for the three variables. The second row becomes 2, 4 minus 3, because these are the multiplying coefficients for the three variables. Now, if you look just at this 3 by 3 array that you have here, let's not use the word matrix for the moment. This 3 by 3 array corresponds to, note it down, the multiplying coefficients in this three linear combinations. Now, after the solid lines, we write the vector, or, well, we write the constants 9, 1, and 0, because these are the three constants to which the three linear combinations are supposed to be equal to. So what we get is what people call an augmented matrix. It's a matrix of coefficients plus the constants. Okay, so what do we do with these things? Well, we try to transform this system of this augmented matrix into a nice form. And how do we do it? Well, we do it by using the elementary operations, which are, this is not a trick question. People at home are screaming the answer, so people in the audience should also scream the answer. We've just used them. What are the three types of elementary operations? You can swap rows, like swap equations. You can multiply by a non-zero number, 1 by a non-zero number, and you can add to a row a multiple of a different row. These are the three operations. Using these three operations, our holy grail is to turn our matrix into a special form. And this special form is called row echelon form. Now, when is a matrix in row echelon form? Well, you have to be able to recognize 1 when you see it, especially in a dark alley at night on Fridays. They can be dangerous. No, they are your friends. So if you see 1, you're happy, because basically you've solved your system of equations. So what are the conditions that a good, honest-to-God matrix in row echelon form should satisfy? First conditions: all rows of zeros should be at the bottom of the matrix. So there may be rows that only consist of zeros, but they should be at the bottom. Why can we assume that they are all at the bottom? Why is this not a loss of generality? Because if they are not at the bottom, what is it that we can do? We swap them and we make them fall to the bottom. You can swap 2 rows without changing the system of equations and the solution to the system of equations. Fantastic. Second condition: the first non-zero entry from the left in each non-zero row is a 1. So you look at each row, the first non-zero entry, if there is one, should be a 1. Again, that's something that we can achieve. By doing what? Which of the elementary operations would you use to achieve this? Suppose that you have a row and the first entry in the row is not a 1, is a 3. Multiply by 1/3. Fantastic. That's one of the elementary operations. We do it, the 3 becomes a 1. Fantastic. Condition number 3, dear friends. There are always 3 conditions when things are really cool. Each leading one, because 3 is the magic number, De La Soul. Listen to that song after the lecture, not now. Each leading one is to the right of all the leading ones in the rows above it. Okay, now we got to look at the matrix. It's not just sufficient to look at a single row. So you look at the leading one in a row, and you look at the leading ones, the first ones that you meet in the rows above it. They should all be to the right. Okay? Not to the left, to the right. Yeah, sort of to the right. I'm doing the right left for you, not for me. Okay? Excellent. So this is what it takes for a matrix to be in row echelon form. Let's test our understanding on examples, shall we? And you know, like a good cook, I had already prepared something in the oven for you before. There you are. Otherwise, it takes 45 minutes at 180 degrees to bake those, more or less. So let's look at matrix number 1. This one. Is this in row echelon form? Your colleagues in the room, as probably you at home are also saying, they said yes. Why? Because, well, all rows of zeros are at the bottom of the matrix. There are only rows of zeros. And all the other mumbo-jumbo conditions 2 and 3, well, we don't need to check anything because all the rows are zeros. So there are no leading ones. Nothing to check. So this is in row echelon form. Fantastic. How about the second one? No, your colleagues are saying, why not? Yeah, because the 0 row is not at the bottom. The 0 row is not at the bottom. But turning it into something which is in, so this is not in row echelon form, but turn it into a matrix which is in row echelon form would be easy. Well, sort of, let's make it better. How about the third one? Sorry? Okay, your colleague is saying, shouldn't the 1 be at the front? Okay, so let's see. Let's see for the conditions. Condition number 1, all 0 rows should be at the bottom. They are. Cool. Condition number 2, if you have a non-zero row, the first one in this case, the first non-zero item that you see is a 1. Cool. It is. Condition number 3. If you look at the leading one, and there is only one, you need to look at the rows above it, and the leading ones there should always be, well, this one should be to the right of those. But there's nothing to check. So this is actually a good matrix. It's in row echelon form. So how about the fourth one? Is it in row echelon form? Yes, it is. In fact, sort of row echelon basically means that if you look at the ones, they should form a sort of nice staircase. You should never go back, essentially, in your staircase. How about the fifth one? No. Why? Because if we look at this entry, for instance, you look above. Oh, yeah, sorry. This is with lipstick on. Sorry, it was indeed a smiley, yes. Now this one has put lipstick on. Okay, so the condition would be to say, okay, we should look above, and all of the leading ones should be to the left. Well, we are okay with the first one, but we are not okay with the second one. So this is bad. No, this is bad, I said. So everything I do, you should apply a not operator on it. This one has mustaches. Okay, so how about the last one? The last one is cool, it's okay, it's kosher, it's in row echelon form. Why? No rows of zeros. The first entry is a 1 in each one of the rows. The first non-zero entry is a 1. And moreover, there is sort of the staircase pattern that we want. So this is okay. The leading digit, the question is, does the leading digit have to be 1? Yes. Absolutely, because you can always make it a 1. You can always make it a 1 by multiplying appropriately that row. So there is a special type of matrix in row echelon form, which is even nicer. And this is called a reduced row echelon matrix. In addition to the three conditions that we had above, it has to satisfy the fourth condition, which is the following. Each leading one, and remember, a leading one is the first one that you meet in any row, should be the only non-zero entry in its column. So let's look back at the examples that we had before. Of the smiley ones, which ones are in reduced form? Okay, so this one is in reduced form, because it is true that each leading one is the only non-zero entry in its column. The third one is also in reduced form, because it's true that the first one, well, because there's nothing to check. Remember, I mean, we are lazy. When there's nothing to check, we are always happy. There cannot be a counterexample. How about the last smiley? The last smiley is not good. Why? Because if we look at this column, there is this leading one here, and it's not the only non-zero entry. So what would you do to turn this reduced matrix, so this row echelon matrix, into reduced form? Okay, you would add to the first row, as your colleague is saying here, -1 time the second row. And then you would remove this nasty thing here. Okay? Excellent. Now you might say, I mean, wow, what is so special about this form of the matrices? I mean, we've already seen examples. We've seen examples all the way. What is so special? Well, what is special is that the algorithms that use something called Gauss-Jordan elimination to solve systems of linear equations will try to put augmented matrices into reduced row echelon form. Because once you've done that, you can read off the solution if one exists straight away. And you will also figure out whether the solutions are just one or infinitely many. Now, this is what you will see in the books, infinitely many, but we are cool computer scientists, and we know by now that since the variables range over real numbers, infinitely many means uncountably many, not countably many. There's more than 1 degree of infinity, as we all know. Okay, so it's time for a break now, even though we already had a break because of Google Hangout problems. We take a break, and after the break, we are going to see the algorithm at work. Okay?